Right. Today we are going to discuss two types of queuing models, specifically the MD1 and MMS queuing models. So far we have mainly seen the birth and death process, and thereafter we have seen MM1 queuing models and various examples of MM1 queuing models, various other issues. But let us now go ahead with variations in them, and two very important systems which we need to really look into. One is the MD1 models and the other one is MMS queuing models when there are multiple servers. Right, MD1 is still a single server, but it is a deterministic model, the service is deterministic. In MD1 model, what happens, the arrival rate is Poisson, but the service rate is deterministic. What is the difference? The service rate is not probabilistic, but it has got a fixed value. Sometimes what happens, the service rate is going to be exactly the same, particular, suppose it is a computerized service system, and as long as you give your inputs correctly and things are more or less in order, then all the service time will be exactly equal, right. Will it make a difference? That is what we are going to examine, that is, supposing the service rate is not probabilistic, it becomes deterministic, then what exactly happens under such situations. We are not going into the details of calculations, but we shall really evaluate at steady state parameter values, particularly the 4 parameters that we know. One is the number, expected number in the system, that is L, expected number in the queue, that is LQ, the waiting time in the system W, and waiting time in the queue, that is WQ. So, what really happens in MD1 model, that is, the since the service is deterministic, we find that the LQ, the expected number in the queue, LQ becomes half of the corresponding LQ value of the MM1 system, right. So, for an MD1 system, the LQ, suppose we call these LQ as LQ1 or LQ2, then this one we call LQ1. So, LQ2 equal to half of LQ1, LQ2 for MD1, LQ1 for MM1. So, what will be the value of LQ2? LQ2 will be half of rho square by 1 minus rho, right. So, it should be rho square by 2 into 1 minus rho. So, what will be the L2, that is expected number in the system, we know this is equal to LQ2 plus rho. So, it should be rho plus half into rho square by 1 minus rho, right. So, that will be the L2, and other parameters, that is W equal to L2 by lambda bar W2 and WQ2 is LQ2 by lambda bar, right. So, those are the waiting times. So, you can find out all the 4 parameters basic parameters of a queuing system, that is expected number in the system, expected number in the queue, waiting time in the system and waiting time in the queue once we know the LQ value, right. So, LQ will be exactly half of that of MM1 system. So, this much result if you remember, then you can easily work out all this, right. So, again once I look here, LQ is half and L equal to LQ by rho, and this is how they work, right. So, this is MD1 model. Now, let us take an example. Arrival to an airport with a single runway are Poisson distributed with a rate of 30 per hour. The average time to land an aircraft is 90 seconds and this time is exponentially distributed, right. So, find the utilization of the runway and the steady state parameters L and W, average waiting time in the system. Will your answer change if time to land an aircraft is a constant equal to 90 seconds, and if so, by how much? Is it all right? So, let us look at this particular problem. So, in this case, the first is, let us write down the MM1 system. MM1 system, we have got lambda equal to 30 per hour and 1 by mu equal to 90 seconds, right. 90 seconds equal to 90 by 60 minute or 3 by 2 minute. So, mu equal to 60 by 3 by 2 equal to 40 per hour, right. So, that is the lambda and mu. So, what will be the value of rho? Rho will be lambda by mu, that is the utilization factor is 30 by 40 or 3 by 4. So, that is the value of rho. So, rho is obtained. Now, what will be the steady state parameters L, length of the system? L will be, so L, that is the total number in the both waiting and also in service. L will be rho by 1 minus rho equal to 3 by 4 by 1 minus 3 by 4 equal to 3, because 1 by 4 other side. And what will be the value of W? W will be L by lambda bar, but lambda bar is nothing but lambda because all lambdas are equal. So, it should be 3 by 30 or 1 by 10 hours, which is equal to 6 minutes, right. So, these are the results that we got, L equal to 3 and W equal to 6 minutes. So, let us look at, these are the results, quick revision. Arrival rate is 0.5, service rate is 2 by 3, then these rho equal to 75%, L equal to 3 aircrafts and average waiting time 6 minutes. What happens in the MD1? In MD1 system, lambda and mu remains the same. So, rho is lambda by mu equal to 30 by 40 equal to 3 by 4. What will be the value of LQ? LQ equal to rho square by 1 minus rho equal to 3 by 4 whole square plus 1 minus 3 by 4 equal to 9 by 16 into 4 by 1 equal to 9 by 4. So, that will be the value of LQ. So, what will be the value of L in this case? L will be LQ plus rho equal to 9 by 4 plus it will be 1/2 of, so we have to take that. So, 1/2 of, so it will be half into, then half into, so it will become 9 by 8, right. So, LQ plus rho 9 by 8 plus 3 by 4 equal to 9 by 8 plus 6 by 8 equal to 15 by 8, right. So, 15 by 8 it will become 1.70. So, 7 means 8, 64, so 675, 1.875 aircrafts, right. So, this is become L, and what will be the W? W will be L by lambda bar equal to L by lambda equal to 15 by 8 divided by 30, right. So, it will be 1 by 16. One by 16. One by 16 hour, which is 60 by 16 minutes, right, or in other words equal to 15 by 4 minutes, 3 point something. So, look here the differences. The differences are very interesting to note, whereas for MM1 system L equal to 3 and W equal to 6 minutes. For MD1 system we get L equal to 1.875 and your W equal to 3.75 minutes. So, what is the advantage that we got? For if we can make the service deterministic, mean other word, if we can remove the variations from the service, we can actually bring down the values of the what you call the number in the system as well as the waiting time substantially, right. So, if you really want to improve the queuing parameters, one method is really add more servers, improve upon, but if you can also remove the chance variations, right, particularly if you can through computerization or any other means, if you can really make the service more what is called deterministic, things will improve drastically, right. So, this is what is shown in the MD1 consideration: arrival to an airport with a single runway, Poisson distribution, and time to land is constant 90 as a constant. So, here rho is 75%. So, look here how the L is calculated: rho plus half into rho square by 1 minus rho. So, rho square by 1 minus rho is the usual LQ, take half of it and then add rho to get the L, because it is an MD1 system. So, it comes to 1.875 and average waiting time is 3.75. So, this is the reduction or advantage that we have got from MD1 consideration. Just for practice, let us take one more example. The cars arrive at a service station at an average rate of 1 per 3 hour period, right. The average time the mechanics require to fix a car is about 1.5 hours. If the arrival is Poisson and the service time is exponentially distributed, find the utilization of the service station and the average waiting time of a car in the service station. Will your answer change if time to fix a car become constant equal to 1.5 hour, and if so by how much, right. So, in this case really what is happening, the utilization of the service time and the average waiting time of the car in the service station. So, let us look at these figures. So, here what happens in this problem, it is a single server MM1 queue. The arrival rate of cars, the lambda is 1 per 3 hours. So, 1 by 3 per hour, right, and the service rate is 2 by 3 per hour. So, what is the utilization? Utilization rho is equal to lambda by mu is equal to half, 50%, right. And what will be the length of the system? The length of the system will be L, which is rho by 1 minus rho, half by 1 minus half, it comes out to be 1 car. And average waiting time of the car in the system W, L by lambda is equal to 3 hours. What happens if we do what is known as the MD1 consideration, right? We have seen that in this MD1 consideration for this problem, we have seen the lambda equal to 1 by 3 and mu equal to 2 by 3. So, rho equal to lambda by mu equal to 1 by 3 by 2 by 3 equal to half. So, that is equal to rho. So, what will be the LQ in this case? The LQ will become half of rho square by 1 minus rho equal to half into half square by 1 minus half equal to half into 1 by 4 by 1 by 2 equal to half into 1 by 4 into 2, is it not? So, equal to 1 by 4. So, this is LQ. So, what will be L? L equal to LQ plus rho equal to 1/4 plus half equal to 3 by 4. Compare these L, the earlier L was 1 car, now L becomes 3 by 4 car, right. And what is the waiting time? Waiting time will be L by lambda equal to 3 by 4 divided by 1 by 3 equal to 9 by 4, right. So, it will be 9 by 4 hour. So, let us look at all these results once again, how we get that once again that rho equal to lambda by mu 50%, length of the system L comes out to be rho into half rho square by 1 minus rho 0.75 car, right, 3 by 4 cars we have got, and average waiting time in the system W is L by lambda is 3 by 4 divided by 1 by 3 equal to 9 by 4 hours. So, what really happens that L reduced from 1 car to 0.75 car per hour and W reduced from 3 hours to 2 hours 15 minutes, right. So, there is a substantial improvement that we can find out if we can really can stabilize the service or reduce the variations, particularly in the service time. Let us now move over to our second model, that is the MMS model. What is really an MMS model? MMS model is a multiple server model. So, in this multiple server model, obviously certain things will be different. What will be different? If you look at the red diagram, look at the red diagram carefully. The first, when there is 0, when there is the state 0, then there could be an arrival, and arrival will be always lambda, all these things will be lambda, there is no issue. But what would be the service? So, when there is only one person in the system, the service could be mu. But when there are more than one person in the system, the service could be 2 mu, right. and obviously when the servers are s minus 2, it will be s minus 2 mu, when s minus 1, it will be s minus 1 mu, and when there is s server, then onwards it will be s mu. So, since really the system behaves differently when there are s number of servers and when there are less than s number of people in the system. When there are s number of servers in the system and there are more than s number of people in the system, then the service rate will be a constant s mu, there is no issue there. But when the number of people in the system will be less than s, at that time obviously we cannot serve s number of people, we shall be able to serve only less than s number of people exactly to the number that is present. So, therefore, the analysis also will be therefore divided into two parts. One is what happens if there are more than s number of people in the system, and what happens if there are less than s number of people in the system. So, if you look at this way, therefore, the formula really consists of two parts. One part is the I am really not going into the derivation because it will be a elaborate detail thing. All that you have to do again, but the process is the same. Process is the same, that you have to do the equilibrium. That means at 0 the lambda into p 0 equal to mu into p 1. But at 1 what happens? What goes out is lambda into p 1 mu into p 1. What comes in? Lambda into p 0 2 mu, not really, earlier we had taken only mu, 2 mu into p 2, right, that is the balance at 1. Similarly, if you keep doing the balance at different points and then simplify, then we can get all these results. But really speaking, we really do not have to remember all the results, we simply have to remember a few results. What are those few results? The first most important result is that of p 0. The p 0 comes out to be n equal to 0 to s minus 1 lambda by mu to the power n by factorial n, that is the first term, right, and the second term is lambda by mu to the power s by factorial s 1 by 1 minus lambda by s mu. Look here, the lambda by s mu is actually nothing but the rho, which is our traffic intensity. How it compares with the MM1 system? In an MM1 system, the traffic intensity was lambda by mu, and in MMS system the lambda becomes lambda by s mu, right. So, that basic difference, in a MM1 system the traffic intensity was rho equal to lambda by mu, here we get rho equal to lambda by s mu. So, that is one of the difference. The second difference, the p 0 there was a very simple calculation, it was 1 minus rho, but here it becomes an involved calculation. You have to sum over 0 to s minus 1 lambda by mu to the power n by factorial n and lambda by mu to the power s by factorial s 1 by 1 minus rho, right. In this case, however, rho equal to lambda by s mu. So, we differentiate by rho and lambda by mu in MMS systems. What will be the Pn? Pn will be lambda by mu to the power n by factorial n into p 0 till n reaches s, right, and beyond s this factor is lambda by mu to the power n factorial s into c to the power n minus s, right. I mean sorry, this c is nothing but s to the power n minus s p 0, right. So, these are the formula that we shall use for this computing the probabilities. Afterwards, please remember there is only one formula that we need to remember if you want the other parameters. What are those other parameters? The first only formula that we need to remember is that of LQ. The LQ in this case is n equal to s to infinity n minus s p n, and it comes out to be lambda by mu to the power s rho by factorial s 1 minus rho whole square into P0. Before we proceed, we must also remember that this P0 is all these terms to the power minus 1. Sometimes we forget that to the power minus 1. This sum over the first term, sum over the second set of things, and addition of this, which is the sum over all the remaining ones, to the power minus 1, and this minus 1 must be clearly remembered, right. So, that is the value for P0. And then as I said, in MMS model, the LQ formula is what we really require, and rest of the things can be obtained by Little's formula, but do remember that some of the simple results like LQ equal to those L plus rho etc., we should be very carefully should be using those results, right, because here rho is not lambda by S mu, here rho will be lambda by mu, because the other part of the formula is more robust, that is W equal to WQ plus 1 by mu, right. So, from there L equal to lambda W, there you will get that L and LQ relation, right. So, do remember that rho equal to lambda by S mu, LQ equal to lambda by mu to the power S rho divided by factorial S into 1 minus rho whole square P0, right. So, these are the some MMS formula that we shall use. Now, let us look at a particular example of an MM2 system. You see, a small bank has two counters, one for deposit and another for withdrawal of money. Customer arrival is Poisson at 10 per hour to the deposit and 20 per hour for the withdrawal counter. Exponentially distributed service time in each counter is 2 minutes per customer. Find average waiting time of a customer in the system for deposit counter as well as for withdrawal counter with and without pooling. Now, you see this pooling becomes an important parameter. Essentially what it means that if we pool the resources, or in other words if we make the resources together, that means suppose both the counters can do both. Usually what happens, the withdrawal counter can only do withdrawal of money and the deposit counter can only do deposit of money. But if both can do both, that means what? You can go any of the counters. In the first counter you can do both deposit and withdrawal, and in the withdrawal counter you can do again both deposit and withdrawal. What will be the advantage? Sometimes you find that deposit counter is busy, but withdrawal counter is free, and the reverse at certain point of time, right. You can utilize those idle periods and therefore, you can perhaps achieve better results. Let us see the example. What happens without pooling of resources? This is the usual calculation. Arrival is 10 per hour, service rate is 2 minutes, that is 30 per hour, utilization factor rho is lambda by mu, that is 1 by 3. What will be the average number of customers in the system? L equal to rho by 1 minus rho, it comes out to be half, and average waiting time 3 minutes. Similar calculation for withdrawal counter becomes average number becomes 2 and average waiting time becomes 6 minutes. So, summarize, if you do not pool, you basically it means 2 MM1, 2 separate MM1 system, right. 2 separate MM1 system. In the first, in the deposit counter, the average number of customers is half, average waiting time is 3 minutes, and in the withdrawal counter, average number of customers is 2 and average waiting time is 6 minutes. Now, when you pool the resources, then what happens? Now, you see the arrival rate of customers at the counters now become a 30 minutes. Please remember one thing, that is let me draw it here, that is in an MMS system, let us call it MM2 system, let us say an MM2 system, right. In an MM2 system, this is the server and there are 2 servers, right. This is the queuing system, but then we still assume that there is a single queue, right. All these people are waiting, they are waiting in a single queue. This is how we are not really, if there are two separate lines in front of the two counters, then that system is nothing, that is not a MMS system, that is essentially nothing but 2 MM1 system. Please remember that. If obviously, but suppose if these people, if they are actually maintaining two queues, but whenever one is free, anybody can go from anywhere, then virtually it becomes a single queue, right. So, must remember that queue is one, there are two servers, people are coming here, they are going out there, and from this single queue they are joining either this server or that server depending on what is free. So, that is the essential idea. Now, let us look at the calculations. So, here lambda becomes the 10 plus 2 equal to 20, that is 30, and service rate at any one counter becomes 2 minutes, that is 30 per hour. So, that is what are the given values. So, what will be the utilization? Utilization will be lambda by S mu equal to half. Now, let us use the formula. The formula is P0 is n equal to 0 to S minus 1 L lambda by mu to the power S by factorial S 1 by 1 minus lambda by S mu. So, you see the first term is, then when you put 0, that will become 30 by 30 to the power 0 by 0 factorial. So, this term is nothing but 1, because you see something to the power 0 is 1 and factorial 0 is 1. So, the first term will be 1 all the time. The second term is 30 by 30 to the power 1 divided by 1, because here lambda by mu are both are same. So, that is also coming out to be 1. The third term is 30 by 30 square, is, you see, this is the third term, 30 by 30, this is the 30 by 30 to the power 2 by factorial 2, and 1 minus half, because this is the half is our utilization factor. So, for a small number of servers, this formula is not that difficult, it is not really that difficult. You see, first term will be 1, second term will be really lambda by mu to the power S by factorial S, and the third term will be the lambda by mu to the power 2, because third term will be, that is in this case only 2 servers, by factorial 2 and multiply by 1 by 1 minus the traffic intensity or system utilization factor. So, it will be 1 plus 1 plus half into 2, this is again 1. So, 1 plus 1 3 to the power minus 1, that is 1 by 3. So, that is comes out to be P0. And what LQ? LQ will be lambda by mu to the power S 30 by 30 square into rho, which is half, and then factorial 2 by 1 minus half whole square into 1 by 3, which comes out to be 1 by 3. So, both P0 and LQ comes out to be 1 by 3, and WQ therefore will be LQ by lambda is 1 by 90, and W becomes what is known as 2.67 minutes. So, look here, the earlier our W was 3 minutes and 6 minutes, after pooling the W becomes 2.65 minutes, right. So, you see that is the kind of advantage that one can really get. So, earlier people were waiting 3 minutes in one queue and 6 minutes in another queue, and later on people are waiting in either queue maximum 2.67 minutes. So, this is what the advantage we get out of pooling of resources. We shall discuss more on pooling of resources and things of MM2 system in our next class. Thank you very much.